one of the easiest to use tools to determine the stability properties of an equilibrium point for a nonlinear system is the method of linearization. Okay, so and the method is such that you are given a nonlinear system and an equilibrium point, let's say the origin, for which you want to determine the stability properties of the solutions, okay, or the equilibrium point. Then what you do is you linearize the system at that particular equilibrium point, obtain the A matrix, and then you check the eigenvalue locations of the A matrix, and depending on those locations, you may or you may not determine whether the equilibrium point is stable or unstable. Okay. Qualitatively speaking, if the linearized system is exponentially stable, then the equilibrium point of the nonlinear system is asymptotically stable. If the linearized system possesses an exponentially unstable solution, then the equilibrium point for the nonlinear system is unstable. Okay, but then there are cases which does not fall into either of the category, and then if that's the case, then the linearization method is inconclusive. So you have to go and apply other methods like Lyapunov theorem and Lassalle's invariance principle, or perhaps Chapayev's theorem. Okay, so this is the linearization method. It's 4.7 in the text. Okay, stability checked by linearization. So consider the autonomous system x dot equals f of x, and suppose that the origin is an equilibrium point with f0 equals 0. So x is in Rn, so f is a mapping from Rn to Rn. Now, assuming that f is differentiable, let A the Jacobian computed at x equals 0. Okay. Then the origin is asymptotically stable. Okay, the origin of the original system x equals f of x. If all the eigenvalues of the A matrix appear on the open left half plane. Okay. If all the eigenvalues are with strictly negative real parts. For all eigenvalues on the line of A. Okay. And the second case where the test works is that if you have just one eigenvalue, at least one eigenvalue whose real part is strictly positive, then the origin is unstable. The origin is unstable if is positive, the real part of at least one eigenvalue is positive, or okay. For at least one eigenvalue of A. Okay. Now, if neither one nor two holds, then theorem stability check by linearization, this method is inconclusive. So we have to go and figure out other ways to determine stability. Okay, so that's important. Let's put it down as a remark. The conditions of the previous theorem, 34.7, are sufficient only. When all eigenvalues are on the closed delta plane for all I, and there exists at least one eigenvalue on the imaginary axis that is real particle 0. Then anything can happen. Theorem 4.7 says nothing. Okay, it's silent. In such case, the origin of the original system, x equals f of x, can display any behavior. It could be asymptotically stable. It could be just stable, but not asymptotically stable, or unstable. Now we're going to consider those counterexamples or those cases over very simple examples, okay? And also through those examples, simple examples, we will also be reviewing our tools that we have seen already for checking stability or sometimes instability of the origin. Okay, so let's begin by the first example. Example, let's call it 1. System is scalar. X dot equals x cube. Okay, nonlinear system. And then the linearization is, now let's write down the state of the linear system by eta. Okay, okay, eta dot equals the Jacobian, okay, f of x, evaluated at, well, the only equaling point is the origin. The origin is our A matrix times eta. Okay, so this is the linear approximation of the system. So what's the Jacobian evaluated to 0? Okay, its partial derivative with respect to x is 3x squared. Evaluate that at x equals 0, so that's 0. Okay, so we have eta that equals 0, so that's our linear approximation. Now, this system clearly is stable. It's not the origin is stable, but it's not asymptotically stable because eta dot equals 0, so that means wherever you start, you always stay there. So the solutions are bounded, but they're not clearly converging to the origin. So we have stability, but not asymptotic stability for the linear system. Okay. Eta equals 0. The origin of the linear system is stable, but not asymptotically stable. Okay. Now, because we have an eigenvalue, because all the eigenvalues, well, because we don't have any positive eigenvalue for the linear system, and because that not all the eigenvalues are with strictly negative real parts, then we cannot apply the previous theorem based on linearization. Okay, so we have to figure out other methods to determine the stability properties of the original system. Okay, so how about the origin of the original system? Okay, the original system state we denoted by x. The linearized system state we denoted by eta. So let v of x be 1/2 x squared. Okay, this is our function v, and let's consider the following set where this function is positive. Set of all x for which v of x is positive. Clearly, this is the entire real line except the origin, because positive everywhere except at the origin. And clearly, u has points arbitrarily close to the origin. We're making that explicit because eventually we're going to be using Chetaev's instability theorem. So for that, let's compute v dot, okay, which is the gradient of v and times the right-hand side of the system, or the inner product with the right-hand side of the system. The gradient is x, and then multiply that by the right-hand side, you obtain x raised to the power 4, which is a positive definite function. v dot of x times x dot, which is x times x cubed, it's x to the 4. Therefore, v dot is positive on r whole intersected with a set of points where v is positive for any radius, okay, r positive. Remember that r whole was defined as the set of points whose distance to the origin is no greater than r, less than or equal to r. So this is the real line, this is the origin, 0. And then we're talking about this set, minus r to r. Okay. So that's r whole intersected with u. Since u does not contain the origin, but everything else, so that's r intersected set. So this is VR intersected by U. Okay. Hence, the origin is unstable by Chetaev's theorem. Okay, so we have a function continuous and 0 is 0. It has points that are arbitrarily close to the origin. Okay. And it's positive, its derivative is positive on the intersection of this set U with the R whole. Okay? And therefore all the conditions are satisfied for the Chetaev's theorem, which means that the origin is unstable. Is unstable by Chetaev's theorem. Because no matter how close you start to the origin, eventually you get out of this set. Well, we didn't have to use Chataev's theorem, but it's good to use it for the review point of view. Okay, so we remember what it was. This scalar system, it can be integrated explicitly, that is, we know exactly what the solution is, so let's write that down. In fact, x of t, the solution, equals the initial condition over 1 minus 2x 0 squared t, and then you take the square root. So this is the solution for any initial condition, okay, x0. Therefore, the system suffers finite escape time. Okay. So the origin is not only unstable, but as, in a sense, as unstable as any equilibrium point can get, in the sense that it becomes arbitrarily large in arbitrarily small lengths of interval. Okay, because suppose that we start from x0 equals 1, then what we have is 1 over 1 minus 2t, and then we take the square root. So this becomes larger and larger as t becomes closer and closer to 1/2, because this becomes closer and closer to 0. And then as you get more and more close, you get larger and larger magnitudes, and eventually at t equals 1/2, you reach, in a sense, infinity. And solutions are undefined for t larger than 1/2, provided that the initial condition x0 equals 1. Okay. So that's one of the examples where the linearization is stable, but the original system is unstable. Okay, that is where the linearization cannot be used. Now let's move to the second example. Example 2. This time, well, it's almost the same system. X dot equals minus x cubed this time. Okay. And linearization is the same. Okay. The derivative of this, or the partial derivative of this, is minus 3x squared. Evaluate that at the origin. You have 0, therefore your A matrix is, because it's a scalar, so it's just 1 by 1 matrix, therefore it's a scalar. Anyways, your A matrix is 0, and since it's 0, the theorem doesn't tell us anything. Okay, linearization theorem. Eta dot equals the A matrix, which is 0 times eta. Again, the origin of the linearization is stable. But now let's do this thing. Okay. So let's try to figure out a way to determine, because linearization cannot be used, to determine the stability properties of the origin for this system. Okay. Let's v of x equals 1/2 x squared. This again use the same v. This time, instead of Chataev's function, this would be a Lyapunov function. So this gives us v dot of x equals x times x dot. X dot is minus x cubed, so that becomes minus x to the 4. So this is a negative definite function. That means it's always positive except at the equilibrium point. So v dot is negative definite, so we can apply Lyapunov's theorem, a positive definite function with a negative definite derivative. Therefore, by Lyapunov's function, Lyapunov's theorem, the origin of the original system is asymptotically stable. Is asymptotically stable. In fact, it's global asymptotically stable because this is a radially unbounded function. Okay, this is again another example where the behavior of the linearization and behavior of the origin system or the solution of the origin system do not match. Now our last two examples are second order, because we have to get a little bit more sophisticated in order to display the phenomenon that I want to display. Okay, for example, 3. Second order system given as x1 dot equals x2 and x2 dot equals minus x1 cube. Okay. Or you can write directly as x1 double dot plus x1 cube equals 0. This is sometimes called the unharmonic oscillator. Okay. Now the linearization that equals x1 evaluated at x equals 0. Okay, times 8. So that's what? Partial of f1 with respect to x1 is 0. Partial of f1 with respect to x2 is 1. Partial of f2 with respect to x1 is minus 3x1 squared. Partial of f2 with respect to x2 is 0, and then you evaluate this at x equals 0. That's 0, 1, 0, 0, 8. Okay, so this is your A matrix for the second order example. So what can we say about the stability properties of the origin of the linearized system? Okay. So this is, all the eigenvalues are at 0, but there's a Jordan block 2 by 2. In fact, the whole matrix itself is a Jordan block 2 by 2 Jordan block corresponding to the eigenvalue on the imaginary axis. Therefore, the origin is unstable. Not perhaps exponentially unstable, but polynomially unstable. There will be some t-term, and it will be moving away from the origin. The solution will be moving away from the origin in a polynomial fashion. So f equals 0 is it's an unstable equivalent for the linearized system. How about the behavior of the solutions of the original system around equilibrium? Okay, let d of x be 1/4 x1 to 4 plus 1/2 x2 squared. Okay. Let's use this as a Lyapunov function candidate, which it is because it's clearly positive, definite. Okay, and it's also radially unbounded. That yields v dot of x equals x1 cube x1 dot plus x2 dot. Okay, the dots x1 dot and x2 dot we can collect from the system equation, and if you do that, you have what? x1 cube times x2, because x1 dot is x2, plus x2 times x2 dot is minus x1 cube. Okay. So this term and that term, they cancel. So what we have is v dot equals 0. So v dot equals 0 means that it's negative semi-definite. So we have a positive definite function with a negative semi-definite derivative. So that means the origin of the original system is stable. However, the linearization, the linearized system, was unstable. Okay, so again, there is a mismatch between the behavior of the linear system and the behavior of the qualitative behavior of the nonlinear system. X equals 0, the origin of the nonlinear system is, by the Lyapunov's theorem, stable. Okay. Now, how about asymptotic stability? If we have a negative semi-definite v dot, then to determine asymptotic stability, what we do is we either go and try to figure out another Lyapunov function, which will give us, if there is such a Lyapunov function, a negative definite derivative, or we move to other methods like Lassalle's invariance principle. But in this case, we don't have to do either of them, because v dot is negative semi-definite in a very special way. That is, it's 0 everywhere. Okay, so it's both negative semi-definite and positive semi-definite. It's a border situation. So that means v is constant throughout the solutions of the system. If v is constant, clearly the state cannot be converging to the origin. Okay, because if the state is converging to the origin, x1 and x2 are going toward the origin, and v of x cannot stay constant. It also has to decrease, but v is constant, therefore the state cannot be going to the origin. So this v dot equals 0 tells us not only the system is stable, but also it tells us that the origin is not asymptotically stable. Okay. But not asymptotically stable because v of x of t is constant. Okay. Again, linearization is unstable. The original equilibrium point, the original equilibrium point is stable. And in our last example, let's modify our third example, example 4. X1 dot equals x2 dot equals minus x1 cube r harmonic oscillator with nonlinear friction or nonlinear damping. Okay. Linearization will still be the same. Okay, for the system. Eta dot equals 0, 1, 0, 0. This time here you will have minus 3x2 squared instead of 0, but when you evaluate that at the origin x equals 0, again you have the same A matrix. Okay? 0, 1, 0, 0. A 2 by 2 Jordan block with eigenvalues on the imaginary axis, therefore the behavior is an unbounded one, therefore the origin for the linear system is unstable. Unstable. How about the origin? Again, let's work with the same Lyapunov function. Let v of x equals 1/4 x1 to the 4 plus 1/2 x2 squared. V dot of x this time yields not 0 but minus x2 to the 4. Okay, so it's negative semi-definite. So that implies V dot is never positive. Okay, V dot is less than 0. Hence, by the Lyapunov's theorem, the origin is stable. And we can now go further by the help of Lassalle's invariance principle and try or attempt to show perhaps that the origin is not only stable but also asymptotically stable. Okay, so for that what we do is we try to figure out the largest set of solutions for which v dot is identically zero. That is, for which x2 component is identically zero. If that set of solutions is singleton, that is, there is only one such solution which is at the origin, then by Lassalle's invariance principle we can be sure that the origin is asymptotically stable. So let's do that. It's an easy check. So what we do is now, to apply Lassalle's invariance principle, we're trying to figure out some special solutions, x of t, for which v dot is identically zero, that is zero for all times. So that means, by definition of v dot, this is identically zero for all times. Therefore, whatever the solution is, its x2 component must be zero at all times. X2 component is identically zero. Now, if this is identically zero, clearly its derivative is identically zero. Okay. And then here is the system. This is the derivative x2 dot. If this is identically zero, so that means this thing is identically zero. We already know that x2 is identically zero. Therefore, x1 must also be identically zero. Minus x1 t cubed minus x2 t cubed identically zero. And because x2 of t was identically zero, so that means x1 of t also is identically zero. Okay. Hence, there is only one solution for which v dot is identically zero. And that solution is this. That is x of t identically zero. That is, we're talking about a solution that sits at the origin, the equilibrium point. Hence, v dot identically zero means x of t is identically zero, and by Lassalle's invariance principle, x equals zero is asymptotically stable. Lassalle's invariance principle. Okay, now let's summarize our observations that we formed throughout the 4 examples. All of the below cases are possible. Okay. This is the origin of the nonlinear system, and this eta is the origin. Eta equals 0 means we talk about the origin of the linearized linear system in the second column. Okay. Example 1, example 2, and we have the last 2 examples. Okay. In the first example, the linear model was, the origin of the linear system was stable, but the origin system was not, in fact, displayed finite escape times. Okay. For the second example, linearized system, or the origin of the linear system, was stable, but not asymptotically stable. However, the original system's origin was asymptotically stable. All the solutions converge to the origin. Okay. And the last two examples, which had the same linearized model, the origin was unstable for the linear system, but in the third example it was marginally stable, okay, the origin, and in the fourth example, the last example, it was asymptotically stable. All the solutions converge to the origin. Okay, so in the nonlinear system, all the solutions converge to the origin. In the linearized model, there are certain solutions which move away from the origin. There are instability. Okay, so therefore, when the conditions in the linearization theorem they don't hold, then we cannot say anything. Okay, the method is inconclusive, so we have to go and figure out the actual behavior of the solutions around the origin through other methods like Lyapunov theorem, Vassal-Murray's principle, and Chetayev's instability theorem. Now, so far we have been talking about the autonomous system, x equals f of x. We started with the definitions of stability, instability, and asymptotic stability, and then we tried to figure out methods, tools to understand those definitions, or sometimes to determine such behavior, to establish such behavior. Okay. Now we will generalize the right-hand side to a non-autonomous case, and we'll say a few words on time-varying but input-free systems. Okay. For which, relatively, the definitions of stability and asymptotic stability, they get a little bit more sophisticated. Okay. So, non-autonomous system. Time-varying systems. This time we talk about the following case: x equals f of tx, and f is a mapping from r times rn. This r indicates the time to rn, and here t is the time, continuous time. What's the definition of equilibrium for a non-autonomous system? It's as follows: x is an equilibrium point if right-hand side at that x equilibrium at that candidate is 0 regardless of t. Okay. If f of tx equal is 0 for all times greater than 0. Okay. And this 0 is, by convention, this is the earliest possible initial time that we can take. It's just by convention. Okay. So stability concept becomes a little bit more subtle for non-autonomous systems because we want certain behavior to be independent of time, even though the system is time-varying, and that forces us to differentiate between stability and uniform stability, or asymptotic stability and uniform asymptotic stability. So what we mean by those words or those definitions is as follows. Okay, now definition 4.4. Let the origin, as usual, be our equivalent point without loss of generality. Of x I tx. Then the origin, equivalent point, is said to be now we introduce certain definitions one by one, certain concepts. It's said to be stable. Okay, now this definition is the same as the definition we're familiar with for the autonomous case. If for each epsilon and initial time there exists delta such that if initially we're not farther away from the origin than delta, then we remain in epsilon neighborhood for all future times. And by future times we mean times larger than t0 for all t greater than equal to t0. Okay. Now for the autonomous system, this delta only depends on epsilon, okay? Because one delta, if delta works for an epsilon at some time, initial time, it will work for all initial times for the autonomous system, because, well, you can always, without loss of generality, you can always take initial time to be 0. Okay. Whereas with non-autonomous system, initial time does matter. Okay. So in that case, delta will depend not only on epsilon but also t0. Okay. So on Monday, given an epsilon on Monday, one delta will work, but on Tuesday, that delta, that same delta will not work. Okay, so delta has to be a function of both epsilon and t0. So here is, let's say, an epsilon, and you give me some t0, and for that, I obtain a delta. This is the origin. And then t0 prime delta 1. And then for some other initial time, perhaps I have to find even a smaller delta, okay, delta 2. And for some other initial time, delta should even be chosen smaller, so that starting from the delta 3 neighborhood, we never leave the epsilon pole and so on. Okay. So that's the definition of stability. And if that definition is not satisfied, or that condition is not satisfied, then the origin is said to be unstable. Not surprising. Okay, unstable if not stable. Okay, and then for many applications, it's reasonable, for instance, or it's desirable that this delta does not depend on the when you start your system. Okay, so in that case, so for a non-autonomous system, that would be a stronger version of stability, and that type of stability is named uniform stability. So the origin is said to be uniformly stable if one delta works for all initial times. Okay, so you give me an epsilon, I figure out the delta, and that delta is still okay for any, even if you change the initial time from t0 to t0 prime, let's say. if for each epsilon there exists delta independent of the initial time t0 such that x t0 less than delta implies x of t less than epsilon for all t greater than equal to t0 and all t0. T0 greater than equal to 0. Okay. And next is asymptotic stability. The origin is said to be asymptotically stable if stable. Furthermore, by choosing delta small enough, you can guarantee the solutions converge to the origin. If stable and for each initial time t0 there exists some constant such that if the initial distance is no larger than c, then you guarantee to converge to the origin as t goes to infinity. And sometimes, for many applications, you would like, or you would like to figure out whether this c actually depends on t0 or not. And that motivates the following stronger version of asymptotic stability called uniform asymptotic stability. Uniformly asymptotically stable if it's uniformly stable and that c doesn't depend on the initial time. Okay, if it's uniformly stable and there exists c and for each d there exists some length of time interval, capital T, such that c and t larger than t0 plus t implies x of t is less than or equal to t for all t0. Okay. So suppose that this is c and starting from magnitudes below c, you always converge to the origin. But now you want that convergence to be uniform. The following says, okay, you have convergence, so that means as time goes on, after a while, you'll be below CO2 line, let's say. And then after a while, you'll be below CO4 and so on. And then this uniform asymptotic stability requires that starting from below C to go to below C2. Okay, we're talking about solutions. Okay, now there will be some time required. Okay, and that time that time should always work for all initial times, t0, okay? No matter from what initial condition you start, the time that is required to go from C to C half is always the same, let's say 20 seconds. To go from C to C over 4, it's always 3 minutes, let's say, things like that. So that's uniform spherical stability. And finally, the strongest definition of all is global uniform spherical stability. And it's the following. Globally uniform asymptotically stable. If uniformly stable, okay, so the origin has to be uniformly stable, so that's one of the conditions. And for each delta, there exists a finite epsilon such that if you start with delta distance to the origin, then you never exceed, never go up the epsilon neighborhood for all 0. Okay, and for each pair CD, like the pair here, C and D, opposite numbers, there exists a fixed time, okay, independent of t0, such that t0 less than c and t greater than or equal to t0 plus t implies norm of solution is less than t for all greater than or equal to 0. Okay. Now the first and the third conditions is clear why they are. Maybe you may be wondering why we need the condition between the two ends. Okay, this one. Okay. And that condition is required if you want, well, this condition clearly wants that, if you want some uniformity for the overshoot. Okay. That is, so you start from below some line, okay, somewhere here, and then after a while you go below something in a uniform way. But there's nothing that penalizes, okay, what you do between from this point to that point, okay, throughout that time, okay. At some time you can make something like this. At some other time you can make something like that. So there's, if you, without that middle condition, there's no restriction on the overshoot, and usually overshoot is something unwanted, or at least you want some uniform bound in it, and the middle condition says that this overshoot always depend on where you start from, or you can always upper bound it by where you start from. Okay. So That's the overshoot condition, the minimum.